So as we mentioned, these things get used a lot in power electronic modules, converting DC to AC or vice versa, depending how it's configured. And some interesting things happen. If you look at something like this, Charles, what kind of spectral content do you expect in a signal like that?
I expect a square wave, a single frequency that I would be turning this on and off at, maybe.
Yeah, so we have the carrier frequency. In that case, it was 2000 hertz. And then with a square, you're going to have harmonics of that. Yeah, sometimes these things show up in our noise and vibration data. In fact, that PWM signal from the power electronics can often have the highest noise or vibration level. Here I got some data. Where is the PWM signal showing up? This is what kind of data here? It's vibration.
I see, I guess that carrier frequency of 5,000, and then, like you said, those harmonics as well.
Yeah, we got a 5,000 hertz carrier frequency, and then we got these so-called switching frequencies that are harmonics. And the motor, it's increasing in speed. So if we were to look at some of the basic orders of the motor, like an electric motor, we got the imbalance of the shaft, and then we have the stators and all this kind of stuff. In this case, the motor is doing what? If the frequency is increasing, the motor must be
speeding up.
Speeding up, yeah. And you can tell it's speeding up. In the PWM, you'll see that the harmonic are getting farther apart. Do you see that here, Charles?
Yeah, I can see that, definitely.
Yeah, so the fact that the switching frequencies get farther apart means we're telling some motor somewhere to increase in speed, and that actually shows up in the noise and vibration spectrum. If you've been looking at some color maps and you're like, well, I understand these orders, they're very traditional, but I see some orders that look like chicken feet. I don't know how you would describe.
You must be hungry.
Yeah, and they're not going through 0 hertz. They're at this carrier frequency. That is power electronics or an inverter that's showing up. And it could be electrical noise, but it could actually be noise or vibration that's induced by the power electronics driving that. Some data with these power electronics, and it's in an active picture. So nice feature of Test Lab, of course, is I can interact with my data within PowerPoint. I got a nice order cursor here, and these are the orders from that motor, right?
Yeah, typical.
And so far, well, if I can make the line, let's make it a little bit wider or something. Okay, now my power electronics are around 5,000 hertz, and they seem to have an order. You know, I'm kind of mystified, Charles. If I want to analyze that, I did put on the numbers there. If I want to analyze this 5,000 hertz PWM signal, what? My order cursor doesn't quite line up. It goes through 0 here always.
Exactly.
What do I do, man?
It'd be nice to have a feature to maybe offset that.
Offset it. What do you mean by offset?
So that it's centered through that carrier frequency, 5,000 hertz would be good.
Oh, like it would be nice if I could just double click on this. Oh, look at that. You can. And so, yeah, if I type in 5,000 hertz, well, look at that, Charles. I can now line up on that PWM frequency and find out what the main harmonics are, etc., to analyze the PWM frequency. That kind of makes sense to you, Charles?
Yeah.
Sweet. Did you know you could do that?
I had tried that before. Very useful.
Now that we're experts on this, I'm going to present some different PWM color maps. We'll see if we can interpret what's going on there. So it's like a quiz, Charles. So what do we have going on here?
I definitely see a carrier frequency. And
yeah, where? What's the carrier?
I don't know. Is that maybe 10,000?
Yeah, and usually a lot of PWMs, 2,500, 5,000, 10,000. So yeah, halfway between 8,000 and 12,000 is 10,000 hertz.
Yep.
This color map was a little different than the other ones. We flipped the frequency axis and the RPM or time axis. That's a feature in Test Lab to swap those around. Okay, so we got a 10,000 hertz carrier. Then what else is happening here?
I see, I guess what we're referring to them as switching frequencies, getting wider initially over the first, maybe half the time there, first 8 seconds or so or something.
Yeah.
And so they're diverging initially. So I guess it was speeding up. Then it started to slow down. It looks like they're converging as we go through.
So the electric motor orders, you'd expect to see them coming down in frequency. When these are converging together, when they're diverging, we're increasing in speed. Yeah, so that's one piece in the gallery of PWM that we have here. Shall we look at another one?
Sure.
That one sold at auction for, we had a non-fungible token with it. No. All right, let's look at this. I could see some PWM in here. So what's going on?
Oh, number one, it looks like the loudest, I guess, we're looking at pressure. The loudest sound pressure is happening related to something with our power electronics there. I don't know, let me see, what frequency is that? 5,000 P? Carrier frequency is that?
It's roughly 5,000, although I think this is kind of a special carrier frequency, so to speak, in that it doesn't stay right at 5,000, right? It meanders.
Exactly.
That's interesting. And it gets loud, and then what happens?
Oh, it changes. Looks like it jumps up.
Yeah. Down here are the electric motor orders. They didn't jump or anything because the motor's still increasing in speed, but our PWM did change, and that's not too uncommon. You can, as you're running these power electronics, you can change the carrier frequency when you want. And the reason they do this, I think of it as like a gear shift. You know how when you're initially taking off at low speeds, you're in a low gear? Yeah. And then as you get up to higher speeds, you get into a higher gear?
Yeah.
Same thing with power electronics. Typically, I believe they deliver more power and maybe are a little less efficient when the carrier frequency is low. And then as you get up in speed, you don't need quite as much power. You want to run a little more efficiency as you start switching at a higher rate, carrier frequency-wise. What we're seeing here with these two different chicken feet, I kind of think of as like it's the shifting gear on an electric motor. And why would we want to increase the carrier other than efficiency and power delivery?
I guess maybe it goes back acoustics from NVH standpoint. It would be less annoying for us or harder for us to hear it at the higher frequency.
Yeah. As acoustics guys, we'd like to see this stuff all be pretty high up where people can't hear as well, switching frequency.